Level 0. Right now, at the center of the galaxy you live in, something is waiting. It doesn't move, it doesn't breathe, it doesn't care. It has the mass of 4 million suns compressed into a space smaller than our solar system. And if you fell into it, the universe's most fundamental laws would stop protecting you. Not slow down, not bend, stop. Its event horizon spans roughly 17 light hours across, wider than the entire orbit of Uranus around our sun. The closest stars to it, a cluster called the S stars, orbit at speeds up to 3% the speed of light. S2, the most studied among them, completes one full orbit in just 16 years. For context, it takes our sun 225 million years to lap the galaxy once. In 2022, the Event Horizon Telescope released the first direct image of Sagittarius A, a glowing orange ring, a shadow cast by something that produces no light of its own. We photographed the darkness itself. The image required a planet-sized network of synchronized radio telescopes to resolve something 27,000 light-years away. It flares. Several times a day, Sagittarius A briefly brightens in X-ray and infrared, bursts of energy from gas clouds and debris spiraling inward. In 2019, astronomers watched it flare to 75 times its normal brightness in under 2 hours. No warning, no explanation that fully satisfies. It settled back down. And here's the detail that stays with you. For a black hole of its mass, Sagittarius A is extraordinarily quiet. It consumes almost nothing relative to its size. Astronomers call it starved. The feeding rate is roughly 1,000 times lower than expected for an object of its mass. That thing is a black hole. Black holes are regions of space-time where gravity becomes so extreme that nothing, not matter, not light, not a distress signal, not a prayer, escapes once it crosses the event horizon. That boundary is where all negotiation ends, permanently. They're born from the collapsed cores of dead stars. They grow by swallowing gas, dust, and anything unlucky enough to pass too close. They range from objects a few miles wide to things so vast they'd consume entire solar systems without noticing. The one in our galaxy is quiet right now. That's level 0, the tutorial. The calm before every single thing on this list gets worse. Sagittarius A is the most well-behaved black hole we know of. That sentence should frighten you more than it reassures you. Level 1. There are somewhere between 10 million and 1 billion of these inside the Milky Way right now. Stellar mass black holes form when a star at least 20 times the mass of our sun burns through its fuel, collapses in under a second, and detonates as a supernova. The outer layers explode outward. The core implodes inward. What's left is a black hole between 5 and 100 solar masses, squeezed into a sphere the size of a city. The nearest confirmed one is Gaia BH1, found in 2022, roughly 1,560 light-years away. We didn't see it. We found it by watching a star wobble. No light, no signal, no warning. Just gravity, pulling something sideways in the dark. These things feed through accretion disks, spiraling halos of superheated gas torn from companion stars, glowing at millions of degrees, screaming X-rays across the galaxy. Cygnus X1 has been slowly draining its partner star for millions of years. Not violent, not dramatic, just steady. The way erosion works, the way time works. When two of them spiral together and merge, they release more energy in a single second than our sun will produce across its entire 10 billion year life. LIGO detected one of these mergers in 2015, not as light, not as sound, but as a literal ripple through the fabric of space-time. Reality shook. We felt it from 1.3 billion light-years away. A billion of them, drifting dark and silent through the galaxy. We've confirmed fewer than 100. Think about that ratio. 1 billion suspected, fewer than 100 confirmed. The rest are drifting out there right now, invisible, patient, indifferent to whether we know they exist. Some may have already consumed nearby stars whose light we're still watching, not yet knowing it's the last light those stars will ever produce. Some of them are closer than we think. We just can't see them yet. It's called cosmological natural selection. Level 2. For decades, astronomers had a problem they couldn't explain away. We'd found small black holes. We'd found enormous ones. But the middle, masses between 100 and 100,000 solar masses, was blank. An embarrassing, conspicuous gap in the catalog. Not because we'd searched and found nothing, because we didn't yet have the tools to look. Intermediate mass black holes hide inside globular clusters, ancient, dense swarms of hundreds of thousands of stars packed at the edges of galaxies. They don't glow, they don't advertise, they just sit in the dark, pulling nearby stars into orbits that are slightly, inexplicably wrong. In 2021, astronomers studying globular cluster NGC 1850 found stellar orbits that no distributed mass could explain. Something dense was disrupting the cluster from inside. Invisible. Concentrated. In 2020, a tidal disruption event in a distant dwarf galaxy, a star being ripped apart by gravity, pointed to a culprit of roughly 50,000 solar masses. One moment, a normal star. The next, a shredded stream of plasma briefly outshines an entire galaxy. Why does this matter? Because intermediate mass black holes are almost certainly the seeds from which supermassive ones grow. They're in their adolescent phase, the ugly middle chapter. Without them, we have no explanation for how the universe built its largest structures. Supermassive black holes were already enormous when the cosmos was less than 1 billion years old. Something accelerated their growth. The leading candidate is sitting, undetected, in globular clusters right now. We're only beginning to find them, which means we've been looking at the universe this whole time and missing entire stages of how the most powerful objects in it were built. The next stage is already confirmed, and the numbers stop making human sense entirely. Level 3. Every large galaxy we've ever examined has one at its center. Not near the center, not orbiting the center, being the center. Sagittarius A, our own, is 4 million solar masses, which sounds enormous until you realize it's one of the smallest examples we know of. Andromeda's central black hole is 230 million solar masses. M87S, the first ever directly photographed, that glowing orange ring that broke the internet in 2019, is 6.5 billion solar masses. These aren't passive objects, they run things. When actively feeding, a supermassive black hole launches jets of plasma at near light speed in both directions, beams extending millions of light years longer than the gap between galaxies. Those jets heat surrounding gas and shut down star formation across an entire galaxy. One black hole deciding how many stars get born, whether civilizations get a chance to exist. The active versions are called quasars. Some outshine their entire host galaxy by a factor of 100. Visible from 13 billion light-years away. We see them as they were when the universe was less than 1 billion years old. Already impossibly large, already impossibly bright. Before our sun existed, before Earth, before anything. How old are you? How old is civilization? How old is the Earth? None of it registers against the timescale on which these things operate. The confirmed kings, the architects of galaxies. And yet, there are things in the catalog that make supermassive sound like an understatement. The next level is where the human mind quietly gives up trying to visualize the scale. Level 4. Ton 618. Write it down. 66 billion solar masses. Its event horizon stretches farther than the distance from our sun to Neptune. Every planet in our solar system, Jupiter, Saturn, all of them would fit inside it. Still room left over. It sits 10.4 billion light-years away and blazes with the luminosity of 140 trillion suns. Our sun has burned for 4.6 billion years and has fuel for another 5 billion. Ton 618 outshines 140 trillion of them simultaneously, just from its accretion disk, just from the gas spiraling in. That disk is a ring of matter heated to temperatures exceeding 10 billion degrees, hotter than stellar cores, blazing across the full electromagnetic spectrum. The brightest sustained object we have ever detected, and it is being slowly consumed by what sits at its center. Here's the part that should make your skin crawl. For a stellar black hole, tidal forces at the event horizon would tear you apart before you ever crossed it. The difference in gravitational pull between your head and your feet, across a boundary just miles wide, would stretch you into a ribbon of atoms. Astrophysicists call this spaghettification, with what we can only assume is dark humor. But Ton 618's event horizon is so vast that tidal forces there are gentle, imperceptible. You could cross it and feel absolutely nothing. No alarm, no sensation. You would simply be at some ordinary, unremarkable moment, inside a region of space-time from which nothing in the universe could ever pull you back. And you wouldn't know. You'd keep drifting forward, comfortable, calm, into a darkness that gets no light, no signal, no news from outside. These objects actually exist. We've confirmed several, and we still don't fully understand how they got this large in the time available. But that mystery is nothing compared to the possibility that some black holes were never born from stars at all. They came from something much earlier. Level 5. 13.8 billion years old. That's how long the universe has existed. In its very first fraction of a second, it was a seething, undifferentiated state, so hot and dense that matter and energy were the same thing. And the physics we rely on hadn't yet settled into place. In that chaos, certain regions may have been dense enough to collapse directly into black holes. Not from dying stars, not from collisions, from the raw density of the newborn universe itself, before any star had burned, before any atom had cooled, before anything we'd recognize as matter existed. These are primordial black holes, ancient, invisible, carrying no record of a star they never were. Their theoretical size range is staggering, from lighter than an asteroid to thousands of solar masses. The tiny ones likely evaporated long ago, but the larger ones, undetectable by any instrument we currently have. Dark, cold, moving silently through the galaxy, affecting everything around them, visible to nothing. Here is the possibility that keeps serious astrophysicists up at night. They might be dark matter. That invisible substance making up 27% of everything, never directly detected, known only because galaxies spin wrong without it. Primordial black holes match the profile exactly. Invisible, massive, interacting only through gravity. Mass windows around asteroid to moon sizes remain that surveys cannot rule out. We might already be swimming through them. The idea that the universe is full of invisible, undetectable black holes from the Big Bang is either the most important discovery waiting to happen, or proof that we've been fundamentally misreading the night sky all along. But solitary black holes, ancient or otherwise, are not the only configuration. Some find each other. And what happens when they rewrite the energy budget of the entire universe? Level 6. Most black holes drift alone, but some find each other. When two black holes form in the same stellar system, or when two galaxies collide and their central black holes are drawn together, something slow and catastrophic begins. They orbit each other. Decades, centuries, millions of years, spiraling inward by fractions, radiating gravitational waves with each pass, bleeding orbital energy into the fabric of space-time itself. Then they merge. In 2015, LIGO detected the first confirmed black hole merger, two objects of roughly 29 and 36 solar masses colliding 1.3 billion light-years away. The signal lasted 0.2 seconds. In that fifth of a second, the merger released more energy than all the stars in the observable universe produced combined during that same moment. Not over a year, not over a day, that same fifth of a second. We didn't see it. We didn't hear it. We felt it. As a ripple just 1,000th the diameter of a proton passing through the 4-kilometer arms of a detector. Since then, LIGO and Virgo have cataloged dozens of merger events. They are not rare. They are happening constantly across the universe. Silent detonations in the dark, each one reshaping local spacetime, each one producing a remnant black hole more massive than either original. Binary black holes at the supermassive scale are worse. When two galaxies merge, which our Milky Way and Andromeda will do in roughly 4.5 billion years, their central black holes sink toward each other and begin the same slow spiral. Supermassive binary systems have been observed. Some appear to be stalled, unable to shed orbital energy fast enough to complete the final merger. Astronomers call this the final parsec problem. We don't fully understand what gets them across the last light year. What we do know is that when they finally close that distance, the gravitational wave burst will be detectable across the entire observable universe. Two black holes patient, circling, waiting for physics to close the gap. Every black hole we've discussed so far hides behind a boundary, an event horizon that keeps its interior sealed from the rest of reality. But mathematics has always allowed for one exception, one type that wears no veil at all. Level 7. Every black hole on this list wears a veil. The event horizon is not just a point of no return, it's a containment boundary. Whatever happens at the singularity, the infinite density, the broken physics, the place our equations refuse to describe, stays hidden. The universe, by apparent design, keeps it away from the rest of reality. This is called cosmic censorship. Roger Penrose proposed it in 1969. Nature does not allow singularities to exist without an event horizon surrounding them. It is not a proven law, it is a hypothesis, and mathematics keeps finding exceptions. A naked singularity is a singularity without an event horizon, infinite density, exposed, directly interacting with the surrounding universe, not hidden behind any boundary, not contained. The Kerr solution, the equation describing rotating black holes, predicts that if a black hole spins fast enough, the event horizon shrinks to zero and the singularity is uncovered. Mathematics doesn't forbid it. It describes it in detail. Whether nature actually produces the conditions required remains unknown and deeply contested. In 2019, a study in Physical Review Letters demonstrated mathematically that certain perturbations could, in principle, destroy the event horizon of a near-extremal black hole, a black hole spinning near its theoretical maximum. The cosmic censorship conjecture held in most cases, but not all. The edges of the parameter space allowed violations. Why does this matter? Because a naked singularity wouldn't just be a point of infinite density. It would be a region where the laws of physics as we understand them break down, and that breakdown is visible to the rest of the universe. Causality, the rule that precedes effect, may not hold near one. Regions around a naked singularity could theoretically allow closed time-like curves, paths through space-time that loop back on themselves. Not a wormhole, not a shortcut, a loop. An event that causes itself, a universe where before and after stop being reliable directions. We have never confirmed one exists, but we have never proven they can't. And the same equations that predicted gravitational waves, black hole shadows, and the bending of starlight leave the door open. Every black hole on this list is hiding something behind its horizon. A naked singularity hides nothing. It simply is, broken, infinite, and fully visible to a universe that has no framework to process what it's looking at. But what if the boundary itself isn't the end? What if the equations that describe black holes have always contained a second structure on the other side, one that was never supposed to exist, and yet falls naturally out of the same mathematics that built everything else? Level 8. Run Einstein's equations backward in time. Out comes a white hole. Where a black hole is a region nothing escapes, a white hole is a region nothing enters. Matter and energy pour out continuously. Anything approaching from outside is repelled. It is, in the most literal mathematical sense, the time reverse of a black hole, an anti-trap, a one-way exit from somewhere we cannot see. This isn't fringe physics. The complete mathematical solution for a non-rotating black hole, the Kruskal-Szekeres extension, contains both a black hole and a white hole connected through what's called an Einstein-Rosen bridge, a wormhole. The white hole falls out of the same equations that predicted gravitational waves, black hole shadows, and the bending of starlight. We didn't add it. It was always there. The reason we don't expect them in nature is stability. They're catastrophically unstable. One stray particle approaching from outside and the solution collapses. Nature doesn't seem to produce the conditions needed to sustain them. But in loop quantum gravity, a serious, peer-reviewed theoretical framework, the story changes. The collapse inside a black hole doesn't end at the singularity. It keeps going, hits a quantum pressure floor, and bounces back. On the other side, in a disconnected region of spacetime, a white hole erupts outward. The black hole and white hole are the same object. Two ends of one quantum event, separated by a boundary we cannot cross or observe. The bounce timescale, from the black hole's perspective, could be extraordinarily long, but from inside the erupting white hole, it might look exactly like a Big Bang, a violent expansion from a single dense point into a new spacetime entirely. In this model, black holes don't slowly evaporate across incomprehensible timescales. They detonate. Every single one is building toward an explosion on the other side of reality. Not consensus. Not yet confirmed, but absolutely not dismissed either. So here's the question that no one can currently answer. If every black hole eventually becomes a white hole erupting somewhere else, what does that mean for what came out the other side of the one that might have started our entire universe? Level 9. This is the one that keeps cosmologists quiet at conferences. In standard cosmology, the Big Bang is the beginning. A singularity, infinite density, the origin point of all space, all time, and everything that would ever exist inside it. But a singularity of infinite density at the start of the universe looks, in the equations, remarkably like the singularity inside a black hole. That parallel isn't coincidental to everyone. A hypothesis, speculative, but published, peer-reviewed, and taken seriously, suggests our universe may exist inside a black hole. Not metaphorically, structurally. The idea, developed by physicist Lee Smolin and others, is called cosmological natural selection. When a black hole forms, a new universe inflates inside it. A baby universe born from the collapse, invisible to the parent universe from which it came. Our Big Bang was, in this model, a black hole forming somewhere else. The physics is not proven, but it's internally consistent, and it produces a testable prediction. Universes that form more black holes produce more offspring. The constants of physics would be tuned over cosmic generations toward producing black holes efficiently, which is exactly what our universe does. The specific values of our physical constants, the fine structure constant, the cosmological constant, the masses of fundamental particles are extraordinarily well suited to producing stars, which produce black holes. That could be a coincidence. It could be anthropic selection, or it could be that our universe is one generation in a long chain, each born inside a black hole, each slightly different, each propagating forward the constants that made it possible. And if that's true, how many generations deep are we?